Imagine you and your best friend each have identical diaries, but you live in different cities, maybe even on opposite sides of the country. Every day, you both sit down at your own desks, open your diaries, and write about what happened. Your thoughts, your adventures, the little details that make up your lives. These diaries are meant to be perfect mirrors of each other, always up to date, always matching, no matter how far apart you are. Each of you records your day, sometimes at the same time, sometimes hours apart. You might jot down a funny story from lunch or a big event you both experienced, but you do it separately in your own words. But here's the tricky part. How do you make sure both diaries always match, word for word, page for page? What happens if you both write about the same thing, but remember it differently? Or if you write at different times and your entries overlap or contradict each other? Whenever you add a new entry, your friend's diary is instantly out of date, even if just for a moment. The same thing happens when your friend writes something new. There's always a gap, a moment when the two diaries don't quite match. Now imagine you both write about the same event at the exact same time, but from your own perspectives. Whose version should go into the official diary? Is one more accurate, or do you try to merge both stories together? And what if one day your friend's internet goes down or your phone loses signal? Suddenly, you can't share your updates right away. Your diaries start to drift apart, each one telling a slightly different story. When you finally reconnect, you both have new entries the other hasn't seen. Some might even contradict each other or cover the same event in different ways. Now you have to figure out how to combine your updates, fix any conflicts, and get your diaries back in sync. What started as a simple project, just two diaries, has turned into a tangled web of information with crossed out lines, sticky notes, and confusion about what's true and what's missing. The more you write, the messier it gets. This small personal challenge is actually a miniature version of a massive problem in computer science: how to manage data that lives in many places at once. Every social media app, every online game, every bank transaction faces this same challenge, but on a global scale. Whether you're posting a photo, sending a message, or transferring money, the system has to keep your information correct and up to date, even when millions of people are doing the same thing at the same time. So how do we keep information accurate and accessible when it's scattered across the globe, moving through cables and satellites, and constantly being updated by people everywhere? The answer isn't as simple as just sending updates faster. There are real limits, like the speed of light, unreliable networks, and the fact that computers can't always talk to each other instantly. That's why engineers and computer scientists spend so much time designing systems that can handle delays, conflicts, and even mistakes. They have to plan for the unexpected and build ways to recover when things go wrong. In this series, we'll dive into the fascinating world of distributed systems and discover how we build technology that works, even when the world is messy and unpredictable. That's the story we're about to explore. Welcome to the world of distributed systems, a collection of independent computers working together as one. Think of your favorite streaming service. When you press play, the video isn't coming from one supercomputer, but from servers all over the world. The system sends you the film from the nearest server, making streaming fast and smooth. All those servers form a distributed system, hiding the complexity from you. Why do we use them? For resilience and scale. If a server in London fails, another in Paris takes over. This is fault tolerance. As more users join, we just add more servers, not bigger ones. Distributed systems power everything from social media to online games, but spreading data creates tension. How do we keep it correct, available, and running even when parts can't communicate? This is the heart of distributed computing. Let's dive in. First up, consistency. In distributed systems, consistency means every user sees the same up-to-date data. Imagine booking the last seat on a flight. Two people click book now at the same time. A consistent system instantly decides who gets the seat and updates everyone. This is strong consistency, a single source of truth. For banks or voting systems, this is essential, but perfect sync is hard. The system might lock data while updating, making others wait. If updates must reach servers worldwide, everyone waits for confirmation before unlocking. If a server goes offline, the whole system might pause, waiting for a response. This is the price of perfect consistency delays and possible downtime. Sometimes, to stay correct, the system must stop and wait, That's the trade-off. Consistency comes at a cost. Next, let's talk about availability, one of the most important promises a digital system can make to its users. An available system is always there for you. It responds to your requests, no matter what, even if the information it gives you isn't the absolute latest update. Think about your favorite social media app. When you open it, your feed loads right away. Even if some of the posts or notifications are a few seconds or even a minute behind real time, the system is always online, always working in the background to make sure you get something rather than nothing at all. Compare this to a system that prioritizes consistency above all else. That system might refuse to show you anything if it can't guarantee the data is perfectly up to date, resulting in frustrating error messages. For most websites and apps, this trade-off is worth it. Users would rather see slightly outdated information than be blocked by an error. For example, seeing a like count that's a minute old is still satisfying, and it keeps you engaged rather than being interrupted by a technical glitch. The main goal of availability is to keep the service running smoothly, even if some parts of the system are experiencing issues or are temporarily offline. If a data center goes down, the system is designed to find another route, another server, or another copy of the data to keep serving you without interruption. It's all about promising uptime and a response so you can rely on the service whenever you need it. Of course, that response might not always be the most consistent or the most up-to-date, but it's better than nothing. That's the deal with availability. You get an answer even if it's not the freshest. In a world where being connected matters most, that assurance is often exactly what we need. Now, partition tolerance. A partition is a break in communication. Servers split into groups that can't talk. Imagine our diary writers again. If the internet goes down, they're in separate partitions. This happens all the time. Cables break, servers crash. Partition tolerance means the system keeps working, even when parts can't communicate. A system without it is fragile. One break and it's down. Real-world systems must handle partitions. It's not optional. So when a partition happens, you face a choice. Do you keep the data consistent and risk going offline, or do you stay available and risk some inconsistency? Partition tolerance is required, but you must choose between consistency and availability during a split. That's the core dilemma. What do you prioritize when the network breaks? This is the heart of the CAP theorem. It says you can only have 2 out of 3: consistency, availability, and partition tolerance. When a network partition happens, you must choose stay consistent or stay available. Imagine servers split into Group A and Group B. They can't talk. If you choose consistency, Group A refuses updates until it can sync with Group B. Some users get no response. If you choose availability, Group A accepts updates, but Group B doesn't see them. Users get different answers. You can't guarantee all 3 at once. This is the fundamental trade-off in distributed systems. Do you stop working to stay correct or keep working and risk being out of sync? Every system must make this choice. The CAP theorem is a law, not a suggestion. It shapes every major online service. You can't have it all. This choice isn't just theory. It's a real decision for engineers, one that shapes how our digital world works behind the scenes. Every time you use an app or website, someone has weighed the pros and cons of these systems to deliver the experience you expect. CP systems, which stand for consistent and partition tolerant, always choose correctness over uptime. They make sure that the data you see is always accurate, even if it means the system has to pause or go offline for a while. If a network partition happens, say a connection breaks between servers, CP systems may stop serving requests rather than risk showing you the wrong information. This can be frustrating, but it prevents bigger problems down the line. Banking systems are classic CP examples. Imagine checking your account and seeing 2 different balances at 2 ATMs. You'd rather see an error or an out-of-service message than risk losing money or making a mistake. On the other hand, AP systems, available and partition tolerant, prioritize staying online, even if it means the data isn't perfectly up to date everywhere. They're designed to keep serving users no matter what. During a partition, all parts of an AP system keep working independently. This means you can keep posting, liking, or shopping, even if the system is temporarily out of sync. The trade-off is that you might see slightly different data in different places. Social media platforms are classic AP systems. Your like or comment might not show up instantly for everyone, but the service never goes down. the experience is smooth, and you can keep interacting with friends in real time. When the network heals and connections are restored, AP systems catch up and synchronize all the data. This process is called eventual consistency, and it's how these systems make sure everyone ends up on the same page. Most large web applications like e-commerce sites and social networks lean toward AP. For them, being available and responsive is more important than having every single piece of data perfectly in sync at all times. For example, seeing a product stock count that's a minute old is usually better than not being able to shop at all. Users prefer a small delay over a total outage. Ultimately, the choice between CP and AP depends on what matters most for your users and your business. Is it more important to always be correct or to always be available? There's no perfect answer, only the right trade-off for your needs. Every system is unique, and the best choice is the one that fits your goals and your users' expectations. That's the reality of distributed computing. It's all about balancing priorities, making tough decisions, and building systems that work best for the people who rely on them every day. These trade-offs are built into the databases powering the internet. MongoDB is a CP system by default. It prioritizes strong consistency. It's great for e-commerce or content management where correctness matters. Cassandra, built at Facebook, is an AP system, always available even if data is briefly out of sync. It's perfect for logging or IoT data, where uptime is critical. Amazon DynamoDB is another AP system, powering shopping carts that must always work. Sometimes, temporary inconsistency is better than lost sales. Many databases are tunable. You can pick strong consistency for passwords, eventual consistency for profile pictures. This flexibility lets developers balance needs for each use case. But the cap trade-off always remains. When a partition happens, you must choose consistency or availability. The database's design reflects that choice. That's how the cap theorem shapes real technology. So why does this matter to you? The cap theorem isn't just for computer scientists. It's a law of the digital world. It explains why your favorite game has maintenance or why social media sometimes shows old data. These are engineering choices, not bugs. Understanding cap gives you insight into the tech you use every day. For future technologists, it's essential knowledge. It forces you to ask, what matters most for my users? Perfect data or always-on service? This decision shapes every system you'll build. The cap theorem teaches us that in any complex system, you can't have everything. You must make choices and design within real-world limits. And that's the secret behind the world's most powerful technology. If you learned something new like the video, share your thoughts in comment section and don't forget to subscribe the channel for more related videos.